Hi everyone, I am Ana Fatima G. Makasindig.
And I'm Sohaima B. Haji Hassan.
And my name is Raisha Hanifa S. Shakiin.
And today we're going to talk about the VISPER model.
That's short for valence shell electron pair repulsion theory, which helps us predict the shapes of molecules based on how electrons arrange themselves.
By understanding molecular geometry, we can explain why molecules have different shapes and how this affects their properties in real life.
So join us as we explore how the VISPER model works.
Let's now get started.
But first, let's have a quick recap on how to draw Lewis structures as it is fundamental for understanding molecular bonding.
First things first, we need to calculate the total number of valence electrons. So these are the electrons in the outermost shell of each atom. And it can be seen in the periodic table.
Right. For example, in something like water, oxygen contributes 6 valence electrons and each hydrogen contributes 1 for a total of 8.
Next, we arrange the atoms. The least electronegative atom usually goes in the center, unless it's hydrogen.
We connect the atoms with single bonds. Each bond represents 2 electrons.
Then, we distribute the remaining electrons as lone pairs around the atoms, starting with the most electronegative ones to satisfy the octet rule.
If we run out of electrons before everyone has an octet, we form multiple bonds like double or triple bonds.
And finally, we should check the formal charges to make sure we have the most stable structure.
Aside from Lewis structures, there are also some more terms to be familiar of. These are molecular geometry, electron groups, and electron group geometry.
Molecular geometry is the arrangement of atoms of a molecule in space. Electron groups are the unshared electrons and single unpaired electrons around the central atom. Electron group geometry is the 3D arrangement of electron group in space. So this is the basic electron group geometries.
Linear has two number of electron groups. Trigonal planar has 3, tetrahedral has 4, trigonal bipyramidal has 5, and octahedral has 6.
We are now familiar with the important terms and thus we will properly start on how to predict molecular geometry using the VISPER model.
This is how we figure out the 3D shapes of molecules.
And it is really important because a molecule's shape affects its properties, like how it reacts with other substances.
The VSEPR model states that the best arrangement of a given number of shared and unshared electrons is the one that minimizes the repulsion among them, or simply how electron groups arrange themselves to minimize repulsion effect from one another.
Exactly. And it's because electron groups are negatively charged and naturally repel each other. They want to get as far apart as possible.
And it's not just about any electron group. Lone pairs, as how the order of repulsion between electron groups show, spread out more than bonding electrons, so this is crucial for understanding molecular shapes.
Right, it's all about the strength of repulsion.
Let us take water, H2O, as an example. Oxygen, the central atom, has two bonding pairs and two lone pairs. With two lone pairs, the repulsion is even greater, squeezing the bonding pairs even closer. Continuing, the first step as shown is to draw the Lewis structure of the molecule.
Once we have the Lewis structure, step 2 is to determine the number of electron groups around the central atoms.
Electron groups are either bonding pairs, which are the electrons in the bonds, or lone pairs, which are unshared electrons.
Finally, step 3 is to determine the molecular geometry using the VSEPR model. We use tables like 15.2 and 15.3 to help us figure out the shape based on the number of electron groups and lone pairs.
This is the table 15.2 and this is the table 15.3 to be further discussed.
As shown in the table, the first molecular geometry is linear, and as mentioned, it has two number of electron groups. This is what it looks like, which is its electron group geometry. formula is AX2 and the bond angle is 180 degree. Let us give beryllium chloride as an example, or BeCl2. It has 0 lone pairs and 2 bond pairs. It also follows the formula AX2 and has the bond angle 180 degree.
Next, we have trigonal planar. This geometry arises when a central atom is bonded to three other atoms in a flat triangular arrangement with 120-degree bond angles. The formula is AX3. BF3, boron trifluoride, is a perfect example. It has 0 lone pairs and 3 bonding pairs. The bond angle is 120 degrees. Boron, the central atom, is bonded to 3 fluorine atoms, creating a trigonal planar molecule.
Introducing one lone pair and two bonding pair, the geometry changes to angular or bent, still under trigonal planar. While still having 3 electron groups, the formula is now AX2E. The lone pair pushes the bonding pairs closer, resulting in a bond angle slightly less than 120 degrees. SO2 sulfur dioxide demonstrates this. It has one lone pair and two bonding pairs. The bond angle is approximately 120 degrees. The sulfur atom, the central atom, has one lone pair and is bonded to two oxygen atoms, leading to a bent molecular shape.
Tetrahedral geometry occurs when a central atom is bonded to 4 other atoms, resulting in a three-dimensional pyramid shape with 109.5 degree bond angles. The formula is AX4. Methane, CH4, is a classic example. It has 0 lone pairs and 4 bonding pairs. The bond angle is 109.5 degrees as well. Carbon, the central atom, is bonded to 4 hydrogen atoms, forming a tetrahedral molecule.
Replacing one bonding pair with a lone pair results in trigonal pyramidal geometry under tetrahedral and again with 4 number of electron group. The formula is AX3E and the bond angle is approximately 107 degrees. Ammonia, NH3, demonstrates this. It has one lone pair and 3 bonding pairs. The bond angle is 107 degrees. Nitrogen, the central atom, has one lone pair and is bonded to 3 hydrogen atoms, creating a trigonal pyramidal shape.
Last, for the tetrahedral with 2 lone pairs and 2 bonding pairs, we have angular geometry again, but this time with the formula AX2E2. The bond angle is further reduced to around 104.5 degrees. Water H2O is a prime example. It has 2 lone pairs and 2 bonding pairs. So the bond angle is 104.5 degrees. Oxygen, the central atom, has 2 lone pairs and is bonded to 2 hydrogen atoms, resulting in a bent molecular shape. In conclusion, molecular geometry is all about electron repulsion and minimizing energy.
Lone pairs push bonded atoms into different positions, creating unique shapes.
And that's how we predict molecular structures using VSEPR theory.